Hi everybody. It's been a while since I've done a video on the CPU and system on a chip design that I've been doing, so I thought I would do that now. So since the last time I demoed the Doom design that I had, this is what we've got. We've made a lot of different changes in the underlying system. I'm going to walk through a little bit of the architecture there. But system-wise, I've added this I/O module, some additional serial I/O, real-time clock, a codec, a keyboard PS2 interface, things like that. Make it a little bit easier to interface. It's also got the LED matrix output on this panel as well, though it's not plugged in at the moment. So um, you can see the real-time clock behavior right there, and I can use the PS2 keyboard and get into the monitor input. And I'm going to start up another demo program that I put together. And this is a game that I ported as part of a hackathon recently, and so it does all of its stuff. It's the idea. So this is a basic block diagram of the architecture. We're going to kind of go through all the different pieces in more detail in a series of design videos I'm going to try to do, but I thought I'd start with this block diagram, which is really a simplified version of the top-level module in the Verilog. So in the center, obviously, you see the CPU itself. It's got 32-bit data and address buses, with the top 4 bits broken out and going into a simple MMU. The MMU just at the moment flags simple operations that are invalid, such as accessing blocks that are not registered to any module, and writes that are to ROM elements, that kind of stuff. If it sees any of those, it sends a fault interrupt to the CPU. In addition to the MMU exception, there's a bunch of other exceptions which I haven't really listed here, but interrupts from the I/O module and things of that nature, timer interrupts and whatnot. So moving on from the CPU, the bus that interconnects all these elements is based on the OpenCore's Wishbone specification. I've tried to be faithful to that, and I've used some Wishbone elements. Most of these modules are developed myself, but I used the I2C module from the OpenCore's site, and it worked perfectly fine with no changes. So I feel like I figured the bus spec out. So the MMU itself is combinatorial at this point and just activates the proper module, and also does the various mux operations that have the outputs of those modules go into the appropriate signal and data path elements for the CPU. So I've shown the data mux, but there's a few others as well, like the acknowledgement signal from the devices. That also goes through a similar mux to get to the CPU. Starting over on the VGA module, we've actually got the VGA signals themselves, but what makes this a little interesting is I've decided to put the video RAM, the frame buffer effectively, using a separate SRAM bus that this piece of hardware supports. So instead of having it be accessible directly by the CPU, the frame buffer, it kind of passes all those requests through. So the CPU can access the VGA module, both the control signals and the frame buffer and the palette map and all of those sorts of things, but it interacts with the top-level VGA module, and inside that it has some arbiters and so forth when it needs to. So when we talk about the VGA module, we'll dig into that a little bit more. So the ROM is actually pretty straightforward, and the only thing that's a little interesting about it is that it's actually got two ROMs in here, and through a switch on the board, I can select the normal ROM and a diagnostic ROM. The SD-RAM controller and the level 1 cache, it interacts with the external SD-RAM bus, handles all the refreshing, those kinds of things, and it also buffers the resulting reads and writes in a two-way set associative write-back cache. It uses burst modes for the read and write, which means that it's a little bit more performant, but it's still a fairly basic cache and SDRAM controller. So it refreshes way more aggressively than it needs to. It opens and closes rows more than it really needs to, that kind of thing. So I could make it more efficient, but so far it's just been a learning exercise, so I haven't really bothered. And then finally, the I/O controller is kind of a catch-all for a lot of submodules for serial LCD, the various I2C SPI modules, 7-segment display, the fan, timers, everything. And really, this high-level container, it just does more address breakdown. So it takes another 4 bits of the address bus and uses as selection for all the different submodules. And those submodules can be instantiated one or more times. So, for example, I have 2 or 3, I think it's 3 at this point, serial modules, 3 or 4 I2C interfaces for the different buses, and so on. So that's the high level. Gives you a sense of how the blocks work and how they interact with each other, and then I'll dig into each one as it's in a separate video. So hopefully this was a good start, and I'll see you in the next video.